In the previous class, we have had a look at the construction of the Huffman code. In today's class, we'll have a look at an alternative way of building the same Huffman code. Huffman code, by virtue of being a prefix code, can be represented by a binary tree wherein the source symbols are represented by the external nodes or leaves. To get a Huffman code for a particular symbol, we traverse from the root to the leaves corresponding to this source symbol and adding 0 to the code word every time we traverse on the upper branch of the tree and add a 1 to the code word every time we traverse on the lower branch of the tree. So, let us look at the procedure of building a Huffman code based on the tree concept. Now, we start the building of this Huffman tree from the leaf nodes. Now, we know that the code words corresponding to the two symbols which have the smallest probability are identical except for the last bit. What this means that the paths from the root node to the leaves corresponding to this symbols will be the same except for the last step. This implies that the leaves corresponding to these symbols which have the smallest probabilities will be offsprings of the same intermediate node. So, what we can do is connect these two leaves corresponding to the two symbols with smallest probability into another single node and treat this single node as a new symbol in the reduced alphabet. Now, the probability of this new symbol in the reduced alphabet will be the probability of the offsprings. So, it will be the sum of the probabilities of the offsprings. Now, sort the nodes corresponding to the reduced alphabet and apply the same rule to generate a parent node for the nodes corresponding to the two symbols in the reduced alphabet with lowest probability. So, continuing in this manner, end up in a single node which is known as the root node. Once we get the tree, then to get a code for a symbol, traverse the tree from the root to each leaf node, assigning a 0 to an upper branch and a 1 to the lower branch. Let us try to look at this procedure with the help of an example which we had considered earlier in the class. Now, I have the source consisting of 5 symbols. These symbols corresponds to my nodes. Initially, I sort these nodes in the decreasing order of probability. Doing so will ease the construction of this tree. So, take these two nodes which correspond to these two source symbols S4 and S5 which are having the lowest probabilities. Combine these two nodes and get a parent node. This node is treated as a new symbol in this new alphabet which I get, and the probability of this symbol is the sum of the probabilities of its offspring. So, 0.1 plus 0.1 I get 0.2. Now, I get new symbols in the reduced alphabet corresponding to the new nodes. Again, combine the two nodes which corresponds to the least probabilities So, combining point 2 and point 2, I get another node with the probability of the new symbol to be equal to 0.4. So, I place it on the top of this node and I get a reduced alphabet with 3 nodes. Then finally, I again combine this and this node and get a node with the probability of 0.6, and finally you combine this 2 node to get a probability of 1. So, this is the procedure for building the binary Huffman tree, and if you look at this procedure, this figure looks similar to what we had designed in the last class using the concept of sorting in the list. Now, this same binary Huffman tree which I have got here can be redrawn in a more formal way as follows. I have a root. From the root I have one intermediate node and another node which corresponds to a symbol. Then so, this is a more formal representation of this same binary Huffman tree. So, it is not difficult to convert this to this form, which is a more formal representations of a tree. Now, this is known as a root node, these are the leaf node, or they are also known as external node. This corresponds to an intermediate node. This intermediate node is a parent for these 2 leaves, and then this intermediate node is a parent for this node and an external node or a leaf node. So, this is a grandparent of the leaf node S4 and S5. So, this is a formal representation of a binary Huffman tree for binary Huffman code. At the moment we are restricting our discussion to a binary alphabet, but this can be easily extended to a code alphabet of size other than binary. Now, the next question that comes to our mind is that after I have got this Huffman code for this source, now for the Huffman code for this source can be obtained from this binary tree also. Whenever I traverse on the left hand side it is 0, and whenever I travel on the right hand side it is 1. So, if I want a binary code for S4 it is 0, 0, 1 and 0. So, and similarly for the binary code for S5 would be 0, 0, 1, 1. So, the next question is that this Huffman code which we have got for the source, is it the unique one? Can I design another Huffman code for the same source? And the answer is yes. A trivial extension or a trivial different version of this Huffman code which we have designed for this would be to get another Huffman code by inverting all the bits in the code words which we obtain from this Huffman code, or by exchanging two code words of the same length. This is a trivial way of getting another Huffman code, but a little non-trivial procedure would be to obtain a Huffman code by carrying out some kind of a sorting in a slightly different manner of the symbols in the list for the reduced alphabet, which occurs at every step of the Huffman code. To understand this, let us again go back to our original example which we had taken in the last class. In the last class, we at the first step of the reduction, we had got 4 new symbols for the 4 letter reduced alphabet, S2, S4 dash, S1 and S3, and in that case we had placed S4 dash right at the bottom of the list. Now what we do is basically, instead of placing S4 dash at the bottom of the list, we will try to place the S4 dash at the top of the list. And so this is what I mean by resorting of the list consisting of the symbols obtained for the reduced alphabet at every stage of the Huffman procedure. So by performing the sorting procedure in a slightly different manner, we could have found a different Huffman code, and we try to do this with a example which we had discussed in the last class. So in the first resort which we get in the last class which we had seen, what we do is this time we place S4 dash which has been obtained as a new symbol by combining S4 and S5, and place the S4 dash on the top of the list. So when I place S4 dash on the top of the list, I get a new table which is for the reduced 4-letter alphabet, and now this is the topmost position where I can place in the list, because the probabilities of S4 dash, S1 and S3 are all 0.2, 0.2, 0.2, so it does not make any difference where I place this alphabet, this symbol S4 dash. And now you combine S1 and S3 into S1 dash which has a probability of 0.4. So we carry out the same procedure which we had studied in the last class. So you sort the alphabet S2, S4 dash, S1 dash, and now you put S1 dash as far up the list as possible. So this is a strategy which we will follow. Whenever we get a new symbol, we will try to place that new symbol in the reduced list at the top of the list. We will try our best to put it as far up the list as possible. So when I combine S2, S4 dash and S1 dash, when I have this alphabet, I place it like this, S1 dash which has 0.4. In the previous class we had placed S1 dash below S2, but now I place S1 dash on the top of the list, so I place it higher than S2, and again we give the code words, and finally we combine S2 and S4 dash to get a new symbol, that is S2 dash, and then finally I get reduced 2-letter alphabet, and the code words for S2 dash is alpha 3, S1 dash is alpha 2, and for this reduced 2-letter alphabet, the obvious choice for the optimum allotment of the code word is 0 and 1. So I allot alpha 3 as 0 and alpha 2 1. Once I have allotted 0 to alpha 3 and 1 to alpha 2, then I can reverse my process, that is unbundling procedure, and get the code words for my original symbols. So if we do that, what we get is the code words listed out here from S1 to S5. This is the code which I get when I follow the procedure. Now, and this is the code which we had obtained in the last class. Now, the code which we have obtained today basically can be summarized in this figure. It's very easy to understand this figure. You have the sorting in the descending order, combine these two, place it on the top of the list in the reduced alphabet. So I get this, again combine this, try to place it at the top of the list in the reduced alphabet. So I place it on the top, S1 dash, combine this, I get this, and then allot 0, 1 and unbundle follow the unbundling procedure. Now if we calculate the average code length for this code which we have got, we will find that the average length turns out to be 2.2 minutes per symbol, and the redundancy is, which is defined as entropy minus the average length for the code, turns out to be 0.078 bits per symbol. So in the code which we have designed today and the code which we had designed in the last class, both have the same average length or both have the same redundancy. But there is a little difference between these two codes, and to look at the difference, let us look at the binary trees for both the codes. So on the left hand side I have a binary tree representation of the first code, that is the code which we designed in the last class, and this is the code which we designed today. So if we call this first code and if we call this a second code, then you can calculate the variance for this code and you can calculate the variance for this code. Though the average lengths are same, you will find that the variance for this code, second code, turns out to be lower than the variance of the first code. And whenever we design using the procedure which we have discussed, then that procedure of Huffman code design is known as, the code which we will get from there is known as minimum variance Huffman code. Now which one of these two code is the better one? To understand that, let us look at the practical implication of minimum variance Huffman code. Now in many applications, although you might be using a variable length code, the available transmission rate is generally fixed. So let us see what happens when you have this kind of a constraint. Let us take the same example of, we have the source consisting of 5 symbols, for which we have already discussed the two designs of the Huffman code in the form of first code and second code. Now let us say that we are interested in transmitting the source symbol from this source, and let us presume that this source generates 10,000 symbols per second. Now we know that the average length of both the codes which we have designed, first code and the second code, is 2.2 minutes per symbol or 2.2 bits per symbol. So we can say that we would require the transmission capacity of 22,000 bits per second. So what it means that the transmission channel expects to receive 22,000 bits per second from this source. Now since we are using the variable length coding, the bit generation rate will not be constant, and the bit generation rate will vary around 22,000 bits per second. So usually the output of such a source coder is generally fed into a buffer. Purpose of the buffer is to smooth out the variations in the bit generation rate. However, the buffer has to be of finite size, and therefore, the greater the variance in the code words, the more difficult the buffer design problem becomes. Now, let us look at the same source. Suppose this source was to generate a string of S4s and S5s for several seconds. So, if I have a sequence consisting of S4s and S5s existing for few seconds, then in that case my first code would generate 40,000 bits per second, because the code word length for both S4 and S5 was 4 in the first code, and we are generating symbols at a rate of 10,000 symbols per second. So, and the channel is expecting 22,000 bits per second. So, the buffer has to store 18,000 bits per second. Now, if we had used the second code for transmission of the source symbol, then in that case, since the code word length for both S4 and S5 using the second code is 3-bit, then what it implies that second code would be generating 30,000 bits per second. So, in this case the buffer has to store 8,000 bits per second if the sequence persists for some time. Now, if the same source generates a string of say S2s, correct, then in that case what will happen, that the first code will generate 10,000 bits per second, and since the channel is expecting 22,000 bits per second, so we will have to make, somehow we will have to make up for the deficit of 12,000 bits per second. But if we use the second code, and again if we have the sequence of S2s, then on the channel we will have 20,000 bits per second, and since the channel is expecting 22,000 bits per second, so somehow the channel has to make up for the deficit 2,000 bits per second. So, looking at this example, it is reasonable to say that we should use the second code instead of the first code. So, in a practical scenario, it is very important to go for minimum variance codes, and so when we are designing Huffman code, we should go for minimum variance Huffman code, and the way to design minimum variance Huffman code is to see that we always put the combined letter as high in the list as possible. Now, after having looked at the construction of the Huffman code, now let us try to prove the optimality of Huffman code. Now, to prove the optimality of Huffman code, we will try to write down the necessary conditions that an optimal code has to satisfy, and then show that satisfying these conditions necessarily leads to designing a Huffman code. So, let us look into the necessary conditions which are required for an optimal variable length binary code. So, the first condition which an optimal variable length binary code has to satisfy is, given any two letters Sj and Sk if probability of Sj is greater than equal to probability of Sk, then the code word length associated with the symbol Sj, that is Lj, will be less than or equal to the code word length associated with the symbol Sk. We have justified this in our earlier class too, but let us provide a quantitative proof for this. So, to prove this, consider an optimal code X. Now, consider another code X prime which is obtained by swapping the code words J and K. So, with the code words J and K of X interchange. Now, if we do this, let us calculate the average length for the code X prime. So, the average length for X prime and difference between the average length of original code X would be given by Pi Li I equal to 1 to Q, I equal to 1 to Q. So, when I take the difference, all the terms will cancel except for the two terms corresponding to the code words for the symbols Sj and Sk. So, what I will get here is Pj Lk plus Pk Lj minus Pj Lj minus Pk Lk, and this can be simplified as where Pj is probability of Sj and Pk is probability of Sk. Now, if we say that Pj minus Pk is greater than or equal to 0, and since code X is optimal, what it implies that average length of X dash minus average length of X should be always greater than or equal to 0. So, now if this condition has to be satisfied and if this is there, it implies that Lk should be greater than or equal to Lj, which means that your code X satisfies the condition 1. Now, the second condition which an optimal code should satisfy is that the two least probable source letters have code words with the same maximum length Lm. Now, we have already provided the justification for this in the last class, where we showed that if this condition was violated, then I would get a code with an average code length which is less than the optimum, and it contradicts our assumption about the original optimum code. Next, then the third condition which an optimal code should satisfy is, in the tree corresponding to the optimum code, there must be two branches stemming from each intermediate node. Now, if this condition was not true, it means that if there was any intermediate node with only one branch coming from this node, then we can always remove that branch or compress that without affecting the decipherability of the code, and in the process reducing its average length. So, this condition also has to be satisfied by an optimal code. And finally, the condition number 4 is that suppose we change an intermediate node into a leaf node by combining all the leaves descending from it into a composite code word of a reduced alphabet. Then if the original tree was optimal for the original alphabet, the reduced tree is optimal for the reduced alphabet. Now, if this condition were not satisfied, then what it means that we could find a code with a smaller average code length for the reduced alphabet and then simply expand the composite code word again into a new code tree that would have a shorter average length than our original optimum tree. Now, this would contradict our statement about the optimality of the original tree. Now, we will try to prove this little more quantitatively in the later part of the class today. Now, once we know that these conditions are to be satisfied for an optimal code, let us see how to construct a code based on these conditions. So, in order to satisfy conditions 1, 2 and 3, the two least probable letters would have to be assigned code words of maximum length, let us say LM. Now, furthermore, the leaves corresponding to these letters arise from the same intermediate node. So, what this implies is that the code word for these letters are identical except for the last bit. So, what we can do is consider common prefix as the code word for the composite letter of a reduced alphabet. Now, since the code for the reduced alphabet needs to be optimum for the code of the original alphabet to be optimum, we follow this procedure again. So, to satisfy the necessary conditions, the procedure needs to be iterated until we have a reduced alphabet of size 2 for which the solution is obvious. But this is exactly the Huffman procedure. So, therefore, we can say that the necessary conditions cited which are satisfied by the Huffman procedure are also sufficient conditions. So, in the Huffman procedure, in order to obtain the optimum code for the original source alphabet, the optimum code is obtained for the reduced alphabet in an iterative fashion. Now, this is based on the fact that the code for the reduced alphabet needs to be optimum for the code of the original alphabet to be optimum. So, let us try to prove this quantitatively. Let me assume that at a particular step in the Huffman procedure, we have a alphabet consisting of m symbols. So, let me say that alphabet, denote that alphabet as S m consisting of letters S1, S2, Sm, and for this alphabet I have the corresponding code, let me denote as Cm with the code words given by W1, W2, and let us assume that the associated probabilities with these letters is so my problem is to design an optimum code or to find an optimum code Cm for this alphabet with this probabilities. So, alphabet consists of size m. Now, in the Huffman procedure, what we do is basically we obtain a reduction of this source. So, let us call that reduction of the source as S minus 1 with the source letters given by S1, S2, S minus 2 and S minus 1 dash, where S dash m minus 1 is obtained by combining the source symbols or the letters in Sm, that is Sm minus 1 Sm. I am assuming that we have arranged this in a decreasing order of probability, and the associate probabilities with this are P1, P2, Pm minus 2, if you wish you can even put dashes, but P1 dash is equal to P1, so it makes no difference, and P dash m minus 1 is equal to Pm minus 1 plus Pm. Now, with this code I also have the lengths associated with it. So, let me call L1, L2 up to Lm minus 2, Lm minus 1, Lm. So, with this reduced alphabet I want to have the code, and this code, the code words are given by W1 dash, W2 dash, Wm minus 2 dash and W dash m minus 1, and the associated lengths will be L1 dash, L2 dash, Lm minus 2 dash. Now, from the way we have generated this reduced source from this source, I can write that W1 is equal to W1 dash, W2 is equal to W2 dash, this is equal to Wm minus 2 dash, Wm minus 1 and Wm, they will differ in just the last bit. So, and the common prefix will be the code word of S dash m minus 1. So, this would be given by concave with 0, and this will be given by the common prefix for both of this is the code word for this reduce symbol. And similarly, the lengths here would be same. Here the length will be L dash m minus 1 plus 1 is the only difference of 1 bit, and similarly for length n. Now, once we have written this, let us try to calculate the average code length for the code CM. So, the average code length can be written as this can be broken up as now for I equal to 1 to m minus 2, Li is same as Li dash. So, I can write this expression plus p minus 1, and the length for m minus 1 symbol is L dash m minus 1 plus 1, and similarly the length for the code word corresponding to SM is L dash m minus 1 plus 1. So, this can be simplified as plus now this is nothing but p dash m minus 1. This quantity out here is p dash m minus 1, and pi is equal to pi dash for I equal to 1 to m minus 2. So, I can combine these two terms as one term and write it down as m. And this by definition is the average length of my code C of m minus 1 . So, if you look at this expression, we can say that length Cm differs from average length of C of m minus 1 by a fixed amount independent of C m minus 1. So, this is the conclusion which we can draw. So, what it means that minimizing, this implies that minimizing is equivalent to minimizing So, now we have reduced the problem to one with m minus. So, we are by moving to Cm-1, we have reduced the original problem from m symbols and m probabilities to m-1 symbols and m-1 probabilities. So, for Huffman code, this procedure is repeated iteratively. So, we have proved at any stage, if you want to have the optimum code for the original alphabet, then you can design the optimum code for the reduced alphabet and then go backwards to get the code. Now, the same thing can be depicted in form of a tree, and this would look something like this. So, here we have taken, let us assume that at some stage in the Huffman coding, we have 5 symbols corresponding to an alphabet, and we presume that P1, P2, P3, P4, P5 have been arranged in the descending order. So, this is a canonical optimal code. Now, you can combine the two probabilities P4 and P5 into one node, and I get a new node here, this combined here with the probability here, and then rearrange the probabilities in decreasing order. I am assuming that probability of P4 plus P5 is greater than P2 or P3. So, if I assume this, then when I add it, this probability will be greater than this, and then I can rearrange to obtain the canonical code for, in this case should be 4 minus 4 symbols. So, Q is in this case 5. So, now after proving the optimality of the Huffman code, the next question is that is it possible for us to calculate the bounds for this Huffman code. Now, it is a little difficult to get the exact bounds, but we can get some kind of an estimate for the both for the lower bounds and the upper bounds. The lower bound is not very difficult to find out, because we know that for any code, the average length of the code has to be always greater or equal to the entropy of the source. So, that is also valid for the Huffman code. So, in that case, the average length of a Huffman code, if I call it as H Huffman, will be always greater than or equal to the entropy of the source. Now, to get an upper bound, we will follow a different strategy. We know that Shannon's coding strategy is a form of a uniquely decodable coding strategy. So, and we have also proved that if we follow the Shannon's coding strategy, or it is more popularly known as Shannon's coding, then the average length which we obtain from the Shannon's coding is less than entropy of the source plus 1. Now, for an optimal code like an Huffman code, the length should be less than the length average here. So, it means that because length of a Huffman code is less than the average length of the Shannon code, which in turn implies that it is less than HS plus 1. So, we can say that for the Huffman code also, the average length of the Huffman code will be bounded from the lower side by entropy and the upper side by 1 extra bit entropy plus 1. Now, as I have said that it is possible to find out more tighter bound on the Huffman code average length, but this is a little more involved. So, we will not discuss this in this class, but we can show that this tighter upper bound will be of the form Hs plus P maximum, where P maximum corresponds to the maximum probability of a source symbol in the source alphabet, and this is valid when P maximum itself is greater than or equal to 0.5. But if P maximum is less than 0.5, then the tighter upper bound becomes Hs plus P max plus 0.086. This is for P max less than 0.5. Now, we have also seen that Huffman code will be always providing on the average code length which is less than any other code. So, it is obvious that the Huffman code average length will be less than the average code length obtained from the Shannon's coding. But still it is worthwhile to have a look at the performance comparisons of the Huffman and Shannon coding strategy, and we will have a look at this performance comparison in the next class.